That's very good morning. Once again, we are welcoming all to the 5 days FDP, which is sponsored by AICTE Training and AICTE Learning. So simply it is called as ATAL. So which is one of the very great initiative of AICTE. So this FDP is being conducted from yesterday, and it will go until this coming Friday, that is 28th. This is on robotics. So today we have, in the second session, we have Dr. N.J. Vasa, so Professor of IIT Madras. It is our great pleasure to welcome for this FTP. We welcome you, sir.
Thank you.
Yeah. And so Chennai Institute of Technology was established in the year 2010 by our Honorable Chairman, C.P. Sriram. And today our institute is on the top second position among all other private engineering colleges in Tamil Nadu. So it is our great pleasure to welcome all the participants on behalf of Chennai Institute of Technology and on behalf of ATAL AICTE. So now let me request Ms. Swapna Sai, third year mechanical engineering students, to introduce our today expert, Dr. M.J. Vasa sir. Swapna, you can.
Once again, good morning to everyone. For this session, we have Dr. Nilesh Jayantilal Vasa to deliver a talk on optomechatronic systems. Dr. Nilesh Jayantilal Vasa, Professor, Department of Engineering Design, Indian Institute of Technology, Madras, received his Doctorate of Engineering from Kyushu University, Japan in 1997. He is expertised in instruments and instrumentation, which includes laser technology, remote sensing, optomechatronics, optoelectronic devices, precision engineering and instrumentation, laser-assisted micro-manufacturing. He has over 10 years of experience in teaching as well as in research, and his tireless efforts has made him to achieve honors and awards. He is also guiding research scholars for doctorate under his guidance too. So far, he has published more than 170 journal articles with high impact factors. We are very proud to have you, sir.
Yes, sir. Thank you, sir. Sir is having a lot of experience in teaching and research, so it is very great to have him on this FTP. So please, you can go to the session, sir.
Okay, thank you very much. So
Yes,
I'll start with my screen share.
Yes, sir. Sir, if any issues, so please you can go with this, sir. If any issues, Swapna will interact you. If any disturbances.
No problem.
Okay. Thank you.
Right. If there are any questions from the audience side, please ask me without hesitation in between.
Yes, sir.
Right. Discuss. So good morning to everyone. Right, I'll be discussing about optomechatronic systems and their applications. Of course, keeping in mind that robotics, right, is growing very much, and the applications of robotics are also plenty, and they are also increasing in industries, in medical areas, biomedical areas, as well as in various day-to-day applications, right, in our society as well. And I'm so I have of course my work, I deal with applications of optical techniques, electromagnetic waves, etc., towards sensing, micro manufacturing. So I thought of giving you some ideas on how optomechatronic systems are getting coupled with such robotics applications or similar in similar areas, right? And I'm Vasa from Department of Engineering Design at IIT Madras, and I'll try to quickly give you an overview of how optomechatronic systems are being used. I will also try to explain few applications in terms of how are we trying to implement such ideas in our laboratory as well. So as all of you know, that of course mechatronics is one area which started evolving from 1970s, right? When microcontrollers, right, in 1980s, when they started coming into picture, and the integration of sensors, actuators, and microcontrollers become a very important, right, useful, idea in order to position, control some of the machine tools, devices, etc. However, it started becoming part of various other applications, particularly even in case of home appliances, or in case of some of the advanced equipments, right? Maybe related to space technology, maybe related to defense, etc. So the mechatronics started playing an important role. Robotics, on one hand, right, as a very important area, and mechatronics coupled with robotics is also, right, it has a widespread applications. What I am going to talk is slightly away from the aspects where microcontroller, microsystems, etc. couples. But then I thought I'll give you an overview of how optical systems can also play an important role in order to drive this optomechatronics field, right, for various applications, right? So basically, it's I am going to talk about how, right, integration of optical and mechatronic technologies. Mechatronics deals with mechanics and electronics coupled with controls, programming, right, etc. I will add one more component to that, is optics. Now, when we are going for various applications related to mechatronics, right, we are also looking for making the system, right, compact, right, more fast in terms of its response characteristics, etc. Maybe precise and smarter, etc. And today, maybe we are also going towards autonomous systems. There or electromagnetic based, right, approaches, maybe in a very simple way we can say vision based systems or microwave based systems, etc. Play an important role, right, in this. So if we see that how this optoelectronics systems are growing, or they have grown in last, right, century or so, and how the mechatronics activities have so grown along with it, and how are they getting coupled with each other. So if we start with automation aspects, wherein we would like to see how the lathe machine, this is just a small, right, picture of a lathe machine. So the working tool is, right, is machining the component. It's fine, it's machining. However, if I would like to go for online dimensions measuring, etc., so that was the idea that was thought in, right, 70s, 60s, 50s, 40s, 50s it was evolved, and 60s, 70s it was implemented, that we can use some type of light and get the reflected signal back, and then measuring certain aspects in terms of position, or in terms of displacement, or in terms of time of light, or some other approaches, in order to determine the change in the dimensions of the workpiece as the machine tool works. Now, that was the one starting point, you can say. But slowly, if we consider the mechatronic systems, they become much more important, right? As I told you, that with microelectronics, etc., coming into picture, with microprocessors coming into picture, microcontrollers coming into picture, the systems started becoming much more, right, integrated in terms of mechanical systems coupled with such microcontrollers, etc. and then providing us a fast, precise, right, outcome, right, in terms of maybe displacement, or in terms of position, or in terms of some other functionalities. Of course, the extreme end of such applications that one can think about is when we consider mechatronics. We know humanoid robot or robotic systems, right? That is one aspect. We also know Land Rovers. They are, right. They are deployed in outside our world, right. They go to the extent of, right, understanding the uh, maybe soil, or maybe the surface, etc., of another planet, of another planet, etc. So this has been sent in Mars, on Mars also, right, in 2000, 2002, 2004. And right, we are also trying to attempt in India towards sending such rovers to moon surface and try to understand the topography or some other aspects. Maybe we would like to know what is whether there is a presence of some substance which are useful for our, right, livelihood. Maybe water, maybe oxygen, or etc. etc. Now, such aspects, how do we see? How could we, right, understand? So, for this, the mechatronic systems are coupled with some optical aspects as well. So, if you see how the optical systems have grown with time, then we can easily see over here that in 1950s, right, holography was one aspect. In 1960s and 70s, fiber systems came into picture, lasers came into picture, and coupling of light through the fiber, transmitting it for long distance, or transmitting it without any disturbance, and then try to measure some information, right, remotely, if we can measure. That is one aspect. Then another aspect came into picture in 70s and 80s, right, with the development of microcontroller, microprocessors on one side. On the other side, CCD camera, charge coupled device, image sensors. It's not only point sensors such as photodiode, but it's an array of point sensor, right? Charge coupled device came into picture. So two-dimensional imaging aspects came into picture, coupled with holography. Of course, the advancement is towards three-dimensional imaging. On the other hand, there are many other aspects which also grew, right, on the optical side, coupled with mechatronics side. So magnetic disk, or the next generation is compact disk drive, CD drives, etc., where they use optical techniques for measuring certain parameters, and in order to convert it in terms of numbers 1 or 0, right, binary numbers, and coupled with mechatronic system. It has a very good, very precise mechanical drives, right, electromechanical drives, coupled, right, with this optical systems. So compact disk, etc., came into picture. Then here AFM I have written, which is nothing but atomic force microscope. So the optical systems coupled with atomic force microscope helps us to measure certain micron size, nanometer size, right, features easily. And further advancement has also we have seen in terms of optical MEMS, micro electromechanical systems, which are actuated by using line, or sometimes there are many sensors which are useful, optical sensors which are useful for driving this MEMS devices. And you also know that it's not only CCD image sensor. Today we have, right, metal oxide semiconductor based, right, CMOS sensor available, which can also perform in a way similar to that of the image sensor as such as charge coupled device CCD. However, it has some features in terms of each of this pixel, right, sensing point also has some amplifier connected with it, and hence the signal right characteristics etc. Can be measured very easily. Now it allows us 2D imaging modalities, and furthermore developments are also taking place, which I will try to explain in a few slides. But before we go into details of such applications, let's see how exactly in 1950s, 60s, 70s we were talking about. So there is a printed circuit board inspection, PCB inspection. In PCB inspection, we know that we would like to see the printed circuit board which is being manufactured, whether it has right certain features, right, and functionality, right, matching with its operational requirements, and that can be measured. So one can see that it was a manual, but manual operation takes a lot of time because there are so many tracks, so many points, so many components mounted on the printed circuit board. It's not so easy. So the next stage came into picture, which is slowly, right, now we have even better versions. So here it's a camera system which will try to help us in terms of measurement. So conveyor system coupled with such camera system etc. Came a next generation of right development. And if I see another example, if I can show you, you might have heard about the word coordinate measuring machine, CMM machine, which is helpful in metrology, particularly to measure various dimensional features of the mechanical components which are being manufactured in the industry. Now, previously, those features were being measured, and if in some cases where we would like to measure the three-dimensional aspects, we will try to measure using a touch probe, right? So coordinate measuring machine will use a touch probe, and the touch probe will pick up the position or right, and will then convert it in terms of some features, right, outcome. Now the similar aspects are being taken care without any contact type touch probe. Rather, there is an optical probe. So light comes and it will try to measure. So you can scan this system very fast, right? Because it's a non-contact measurement. Optical measurements which travels very fast. Light will travel fast and return to right. Provides the reflected signal input right with a very short in a short time. As everyone knows, light can travel 1 nanosecond 30 centimeter. So you can imagine that the time taken for signal to observe it can be of the order of a few sub microsecond to few nanoseconds, etc. So in that sense, the scanning becomes very fast. It's a non-contact, so no wear and tear of the tool. Hence, the dimensional precision, etc., can easily be achieved in terms of measurements I'm talking about. So this is another approach, another development which has taken place. Now, all these aspects, what I showed you in the previous slides, are based on optical technique. And so, sometimes we use an optical source which interacts with the object, and the reflected signal, or in some case transmitted signal, or in some case some absorbed signal helps us to determine the characteristic of the object. And optical detector can be used in order to detect either the reflected signal, or in some cases I told you transmission signal, etc. Now, one application, very simple way to determine the position or the right dimensional characteristics of the object is we can use a light, and the reflected signal will be reflecting on the detector. Now, this detector is not if it is a point detector, right? It can give us the information about one particular point over here from where the light is getting reflected. And if the reflected light is reflecting at a point where the detector is placed, we can estimate what is the angle of this. And indirectly, by scanning the light over here, we can estimate the angle or the surface undulations, etc. Other way, in order to make the process even faster, we can have an array of photo detectors, and that also can help us to determine the surface textures or such like scattering or surface modifications very easily. Now, a light can also be used in order to induce some type of heat input in the material, and then because of the thermal expansion due to the laser or light induced heating, we can see the change in the dimensions. Now, changing the dimension is one aspect, but indirectly, what we are observing over here is light laser induced heating and then thermal expansion. That means actuation of this light. It also, the material also act as a small actuator. Now, this actuation can help us in precisely positioning some of the components, right, by very fast heating of such actuator and very fast cooling, subsequent cooling of this actuators. So it can used as a very fast actuator. Of course, the limitations might be, or it would be, is related to the amount of such displacement, which may be of the order of few micrometers or little more. Right. Secondly, although we expect laser heating to be fast enough, and we can see the actuation to be fast enough, but still it takes some time because of cooling cycle, cooling process, etc. comes into picture. Heating is also, is all of you know, right? It takes some time in order to reach to a particular temperature, heating of the material. Hence, the dimensional aspects, right, can also be observed in terms of short time, and we can easily see, right, thermal expansion playing an important role as an actuator through via laser heating of the material. Now, as I was trying to tell you, that laser can also be used to read, right, compact disk data. So this is the cut section of the compact disk, which has some grooves and right, grooves which are marked on this, and whenever laser interacts with the material, the properties of this grooves will change, right? So if the property of this groove changes because of the laser interaction via laser heating, what exactly is changing is the refractive index of this material. So if whenever there is a refractive index change, the reflective characteristics are different. So, for example, you can think that while writing in the medium, you use a little high power light source or a laser beam and focus it and try to change the characteristics. So, whenever the characteristics of this material is changed, end up with registering some information indirectly. Whenever the characteristics are not changed, will also act as the reference. Now, if I can see when I would like to, when I'm trying to read the data from the compact disk, now laser has already based on the data has already changed the surface, right? So whenever I use the light and I see the reflected signal, based on the reflected signal, we can determine whether we are seeing a zero position or whether we are seeing one position. So when the device, right, drives this compact disc and allows the laser beam to scan over, at the time we can easily see that 1010 can be observed with the help of no reflection at the point 1 and maximum reflection at the point 0, or vice versa, whatever way we can think about. So this is indirectly a digitized data storage where we use optical technique coupled with, right, mechatronic systems. Now, just to give you another important point is sometimes we use light source in free space, or sometimes we use it through optical fiber. Now, what optical fiber does is it allows the light to get transmitted through it through via internal reflection. So the light which is getting transmitted through the medium will undergo internal reflection depending upon the refractive index difference between the outside atmosphere, right, outside an ambient medium, and within this, right, a fiber structure. So based on the refractive index difference, the reflections comes into picture, internal reflections, and that allows the light to get transmitted from one end to another end. And as I told you, of course, the speed of light in space is 3 into 10 to 8 meter per second. On the other hand, the refractive index of such glass medium is around 1.5. Hence, if you can imagine that if the light is traveling through the medium, right, along a straight line in a medium, right, along a straight line, then what we can expect, it will be traveling with the speed of light in air or in space divided by refractive index of that medium. And refractive index of the glass, if it is around 1.5, that means this, right, speed of light over here when it is traveling through the medium will be around 2 into 10 to 8 meter per second, right? 3 into 10 to 8 meter per second divided by 1.5, so it's right, 2 into 10 to 8 meter per second. That means light travels very fast through the medium, and means we can transmit the signal much faster. Previously, we all of us know that there were some technologies based on cathode ray tube. Then came plasma display panel, and now thereafter liquid crystal display panels, and now light emitting diode based panels, etc. But so that is this is I am talking about how optical systems can be used in order to. So the picture on the right hand side, what I'm trying to show that the optical approaches can be used to not only to image the object, but also to right, we can make use of it for display purpose as well. So that is one aspect. So first, as I told you, light can be used in order to capture the information from the surface. The second aspect, light can be captured to information from the compact disc, right, surface, and it can also be used to actuate, right, at a micron level also. It can also be used, transmitted through a medium of fiber or optical fibers, etc., which allows fast data transmission, and that too, it allows maintaining certain characteristics of this laser beam which is getting transmitted. Now, it's also possible to use light along with optical switches for basically in order to control multiplexing of the data. Uh, what I mean is that the light will interact with various mirrors in this system. So maybe I have one more slide, I think. No, I think I didn't put, but there are mirrors. Let's say there are array of mirrors, right? So let's say light comes, and if particular mirror stands up over here, the light will get reflected to this position. And if the mirror is standing up in the center, then the light will reflected to this right position. Let's say if the mirror is standing up over here, then the data from the light which is coming along that line will be transmitted. And if the mirror is located here, then the data from the light from here will get transmitted. So basically what I'm trying to say that we can use such micro actuators coupled with light in order to transmit data at various positions as well. So the such micro systems, right, and multiplexer, demultiplexer systems allows coupling of light from various positions, right, to different positions as well. That means data transmission becomes even much more larger, because different it can transmit to different locations and from different positions. So multiplication, right, of the data transmission becomes much more. That's also possible using such optical components coupled with the light. And you can even imagine that if light has multiple different wavelengths, then it can transmit information, different information with different wavelengths at different positions. So you can imagine that the data transmission becomes much more faster, and it can also transmit spatial, right, information, etc. Laser beam can also be used in order to understand the material property variation. By heating the workpiece or by uplifting some material, we should also be able to determine the sum of the characteristics. Now you can imagine that if we couple such optical systems along with the robotic systems, then we can make use of a robotic system coupled with such systems for maybe automatic welding process, or automatic cutting process, or automatic material characterization process, or automatic metrology applications, etc. So all such aspects, right, are coming into picture, wherein the optical systems which consist of light and the sensor systems, right, coupled with, so there is an optical light source, and there are sensors. They get integrated with maybe related to sensor. There will be some noise, so there will be, or some signals, so there will be some signal processing. There will be some mechanisms which will, right, allow the light to be to capture the information from a certain position. So mechanisms, some precision actuators, etc., allows motion control. So optical systems coupled with motion controls, right, and various other actuators, etc., can allow to drive various aspects of the mechatronic systems. However, the system may be slightly complex, because now it requires, right, illumination control, right. A source light is here, so optical source is here. You may need some illumination control to, right, to see through the object, etc. Sensing, as I told you, we need optical sensors to capture the information. Then we also need some type of actuation optical scanning is possible, right? Motion control is possible, visual optical information feedback control and data storage is also possible, right? So, and data transmission as well. Hence, this technology has lots of right applications coupled with robotics, coupled with mechatronics, and hence the word optomechatronics. Now, I would also like to give you some hint that what are the ways that optical systems can work with the material in order to characterize or in order to capture some information. It may be using laser intensity, or it may be based on the directionality of the optical beam, right? Or it may be based on the interference properties. So interference characteristics of the laser can help us to determine various micro positioning movement, right? Using interferometry techniques. So which I will try to explain to you after a few slides. But so it's not only measuring the light intensity, but it's also indirectly helps us to measure the phase difference and the optical path length difference, etc., using such interferometry technique, right? That means intensity, directionality, the optical coherence information, etc., can be captured using various types of optical based sensors, and it can help us to determine position in case of a servo system, of a servo mechanism, DC motor control or servo mechanism. They certainly make use of such optical approaches in order to detect, right, certain information and positions. What type of light sources which are being used? And of course, whatever I have described here doesn't mean that these are the only light sources. There are many other light sources, laser sources, which are being used. But some typical examples, whenever we would like to measure just a small directionality change or spatial information through interference, etc., we don't require many high-powered laser, etc. We can use small power helium neon laser or laser diodes, right? With they are very small in size, few millimeter size, etc. Even smaller in case of laser diodes, etc. So those aspects are used in order to capture the information in terms of speed, right, displacement, or spatial characteristics, or coherence characteristics, or directionality, or intensity change, etc. We will try to see some of these examples independently also in order to understand that, right, how light is trying to help us optical systems. So one approach of the one which I told you here, that we can make use of light based on either the intensity measurement or directionality or interference, or right triangulation technique to measure the displacement, etc. And image processing also is possible. So all these aspects, right, we'll try to see here that we can make use of, let's say there is an illuminator, light illumination is there, and then there is a camera which can capture this reflected signal and help us to define a 2D plot, and then we can make use of such ideas, right, and measure whether the workpiece is damaged or not, whether the operation which we were supposed to do, right, has been performed or not, whether segmentation of the object, etc., can easily be captured using such vision system. So this technique is known as machine vision approach. Here, it's we need some type of light source in order to illuminate the object, right, and then capture the information. Now, as it is written over here, so the technique involves sensing, Of course, illumination and then sensing, pre-processing and removing the noise, etc., and then segmentation, and and then we can also recognize certain features, etc., and interpretation based on these features. I can give you one example that if you would have noticed in any of the recent day supermarkets, you will see that it's apples or oranges are already packed in a pack. Okay, the pack may contain 4 apples or 6 oranges, etc. Now, and there are packs with different price tags. Okay? Of course, the price may little bit vary even with the 4 oranges in a pack because of the size of the orange, which may change. So it's that's information is one information. But if we, it's not that the price is varying just because of the weight of the orange or apple. It is the maybe the sweetness may be different, right? A cheaper, similar, same weight apple may be having a little less delicious taste, right? Or sweetness. So those aspects, how do we measure? Can we measure just by illuminating the light on the object or apple or orange and measure? No, not necessary. We here we can observe the workpiece shape, size, etc., but we can determine the internal characteristic of the object as well, if light can penetrate through this and get reflected, isn't it? So that's possible with scattering in the sense, as I have shown you over here in a simplified way. Light goes through some medium, and whenever there is a scattering medium, the light will get scattered. Okay, and scattered light can also help us to measure certain characteristics, right? That is through, of course, through some type of approach, maybe absorption measurements, maybe transmission measurements, etc. But it's possible. I'll give you a simple example of that. You see over here, the process, the robotic arm is trying to do a welding process, right? A welding. Now the robotic arm is moving along this S path, and when it is moving, it's filling this, right? Well, over here. It's right. So these are the 2 plates, one plate, and this is another plate. They are connected by a butt welding, right, with each other. Now, when the robotic arm is doing such butt welding process, we would like to know that the filling of this weld material is properly done or not, right? Whether the welding between these 2 plates is proper or not. It's not that there is only one parameter to measure. If I really would like to measure the characteristic of this weld part, we may have to do some mechanical testing, etc. However, when the weld process is on, we can still determine certain features, okay, during the welding process itself, which may give us some indication about, right, what is expected, right, what will happen. What happens? Let's say if there is a micro hole or porosity, if we can observe, we can see that, yeah, that is a defect. That means without doing any mechanical testing, we may be able to interpret some aspects. So over here, you can see that if let's say position A over here, when welding is done, you can see that the camera is capturing the illuminated part, and the illuminated part is captured, which is nothing but the weldment. Of course, when welding process is on, when the welding is taking place, the brightness of the weld tool will not allow this camera to capture much information rather than getting saturated. However, when the weld arc is not present, right? What will happen? The light which is reflected from this, if the light from the illuminator will get reflected from this type, right? This position, and it will be captured using camera. What we see that depending upon different positions, right, there will be difference in type of weld made, what we see here, right? So there can be a small hole, etc., and that cannot be captured so easily after the whole welding process is over, because then we'll have to do destructive measurements only in order to capture the subsurface information. There are some ways we can use X-ray technique, which is also one type of UV region, electromagnetic wave, in order to capture this information via transmission studies. But sometimes, in order to see through two-dimensionally and observe the exact correct position, etc., right, becomes difficult. And in this case, the light which is illuminating this object can be captured using camera simultaneously when the weld process is on, and it will help us to determine some of the defects which are very difficult to determine, right? So the cross section of the weld bead after welding is over and after vision guided robotic welding can be seen here. Now it may be clear to you that optical technique is used in the previous case is basically to sense the presence or sense the characteristic of the weld which is being deposited here. Okay, now we will see a slightly complex aspects of such optical techniques for various mechatronic systems. Now here, of course, the system size is of the order of few hundred micrometer. Okay, so each of these loads, what you see here or over here, depending upon their size, etc. But what each of them contains so many components. Okay, micron size. So there is a spun here, right? And there are sun with or other planetary or planet gears, right? And these are all to be placed here, and then we can capture the information when assembly is going on. This is at micron level. So an optomechatronic system which has been built in order to show there is a gripper, there is a micro actuator, gripper system which will place the workpiece, there is a camera system which will observe and which will give the feedback such that the gripper will position the workpiece right, or gripper will pick up some other workpiece from some other beams, right, and bring it here and then position it here, or right, all such aspects are possible using such a flexi micro assembly system, right? So basically there are one optical microscope and imaging system, right, and there are actuators in terms of grippers, micro manipulators, etc. And finally, once the process is over, right, so the whole assembly has to be again placed on some other or assembled or combined with some other assembly. So those operations are the second stage operations. But you can see that the first stage operation is it is possible now with the help of optical based approach, vision based approach, to position the workpiece in micron level. Now I will give you another example where a robotic arm is used, but here robotic arm is used not for pick and gives. Anyway, that will be the main function which it will perform. Okay, it may pick a welding torch and do the welding, or it may pick up a workpiece and assemble, use it in assembly, etc. However, before it goes for assembly station working, whether in automotive factory, before it goes on a welding station for welding a car, body, etc. It has to be calibrated. Okay, the robotic arm should be calibrated, and in order to check its positioning, etc. Right, it should precisely get position every time. Otherwise, we will end up with welding different positions on the car body, etc. So basically, the calibration, positioning calibration of the industrial robot also involves optical systems. Here, what is shown over here is based on a paper which is marked here. What this research team has done in order to develop a robot calibration system for such processes, assembly line robots, welding line robots, etc. is they have used a fixture frame, right, which has its own frame reference, and on the top the position sensor devices are placed. This position sensing device can give us the information of exact position where the light is irradiating the surface. Okay, so there is a laser here. So light from this laser light will strike every this position sensing device, and what it will try to measure is the position sensing device will find out where exactly the light is positioning, right, and that position will help us to determine the exact precisely calibrating the arm system. Now there is another fixture over here which on the same on this fixture there are LEDs which are mounted, light emitting diodes mounted over here on the surface. So those LEDs, when they when they light up, right, what will happen? A camera here will pick up the LED positions now. Okay, and these LED positions are being picked up, but of course the camera system which will pick up this LED position may have a resolution which is of the order of few micrometers or few tens of micrometers. So it is treated as a slightly rough positioning, which is image based visual servo system. And as I told you, there is another fine positioning using position sensing device, which are seen over here. So such position sensing device can do precise location, calibration, etc. of this arm. So that is being done by position sensing device, precise positioning, rough positioning, right, low resolution positioning is done, captured using camera system. So this combination can help us, right, to position of the camera arm, and not only position but also calibrate the system, right. So in order to calibrate, we may have to what is being done, they will change the angle of this arm. However, the light which is being emitted from this laser sensor, laser emitter should will be captured. The position of that on the fixture will be captured using position sensing device. And as you change the angle, still the light will get positioned on this, let's say, sensor device. Then we can measure, right, various such light positions, and from this information robotic arm calibration can be derived. because basically, why do we need calibration? Although we expect robotic arm to be the similar for that system, but the link length may not be exactly the same, right? Same robotic system can have links which are slightly different, micrometer order, depending upon the size, etc., or maybe few tens of hundreds of micrometer order length difference, which is very difficult to capture in the assembly line, but it can be captured very easily and corrected, right? For we can even correct using this equations of lines, we can correct the exact positioning, and finally we can use it, right, for extrapolation and capturing and positioning applications elsewhere. This is the actual system which is being placed. So the robotic arm over here, and how the calibration is being done using the fixture which contains position sensing device PSDs and light emitting device LEDs, and 4 corners, all these corners, etc. 1, 2, 3, 4, and a camera system over here, and a laser system to illuminate this position sensing device, and a camera system to image the light emitted from LEDs, etc. And then we can do precise location, precise calibration using laser and position sensing device, or slightly rough calibration using image right modalities, etc. So that is another application. So now you can see that we were right. You can imagine that we can make use of a system to observe process parameters. We can make use of the optical right-based systems, right, in order to micro assembly system. We can make use of such imaging modalities, etc., along with the lasers or optical LEDs, light emitting diodes, etc., in order to calibrate the robotic systems for industrial applications, etc. Now we can also, as I told you, this is a very first of all, I should tell you very clearly, this is the very primitive, right, atomic force microscope, very primitive system, atomic force microscope. This atomic force microscope, which I'm going to explain, has become even advanced. However, they also make use of optical system in order to capture the information of the position of this tip. The tip over here is, although it is seen as micrometer order or even larger, but actually the tip position will be of the order of few tens of nanometers or even, right, smaller, and it will try to capture the features, right, through the interaction, surface interaction between the probe and the material surface which we would like to measure, and how exactly the information is being transmitted, the position of this probe is being transmitted, is light is getting reflected. So light from this laser, it gets reflected from this cantilever beam arm. Now if the cantilever beam arm, when it moves over the surface, its position will start changing according to the surface roughness or surface texture, etc., and accordingly the light getting reflected to the position sensing detector changes its position. So when it changes over here, we can capture the movement of this cantilever beam over the surface, and this position which is changing can be transmitted, the data from here, right, the optical illumination position from here can be transmitted to this piezoelectric system, PSZT drive, piezoelectric drive, and the drive position can change in order to bring back this AF team exactly along this particular line, let's say. Okay, then this vertical or horizontal movement, right, in either direction can help us to determine the surface texture characteristics, and the precise measurement is also possible, right, using proper micro such position sensor devices, as well as placing them in all the three directions to capture various information in terms of position and angular, right, control. So all 60 position and orientation control can be achieved using such system in the atomic force microscopy measurements. Yeah, I was talking about previously. I was talking about, yes, mirror position, and the light from here will get positioned here. If this mirror is going to observe this line, it will get positioned here. Now, instead of this mirror, if this mirror picks up the light, then another such position, right, can be captured. So all this type of actuation is done, of course, through some other means, piezo actuators or electromechanical actuators. However, optical techniques coupled with this allow us to transmit the data at different positions in XY state. That's why this is known as optical switching MEMS device. This I will skip. You can even use online capture of the imaging modalities in order to determine which particular wheel, right, is being conveyed, and accordingly, depending upon the assembly line requirements, a particular wheel will come and it will get assembled. But while it is moving, it will be right. It will be judged, right, whether the correct wheel according to the correct model of the car is matching or not. So like this, there are a few more examples. I'll skip, but I'll come to very important aspect of fiber optics based sensing. Okay, so before we go to this part, where how optical techniques can be used in order to capture various other information, I would like to just I'll skip this. I would like to come here. I would like to just sorry. Yeah, I know.
It is
No, I know. I would like to just ask audience whether they have any query or any questions, etc. If they have, till now whatever we have dealt, then I can quickly give answer, and then we will move to the next topic for a few more minutes, right?
Sure, sir. Sure, sir. We have a question from Dr. Vel Murugan.
Yeah.
What type of communication is used in this robot?
Okay. So, of course, in this robot means you are talking about the position sensing device, etc. So the optical techniques over here, what I described over here, are basically for calibration purpose. Okay, the data captured using camera or using position sensing device, etc., are being transmitted through electrical means not the optical signal, but the electrical signal is being transmitted, etc. Okay, so the data here transmission is through electrical means. In some cases where there is a remote measurements, we can particularly certain applications where the data transmission through electrical means becomes a little difficult because of the some other interfering signals presence in that surrounding. Okay, So in that case, we can make use of optical fibers to transmit the optical signal, which will not get disturbed by any other electrical or magnetic fields in the surrounding region, and we can transmit the signal very well without getting disturbed. And then subsequently electrical systems are used to photo detectors will be used to convert the optical signal into electrical, and then will be coupled to some type of control loop through microcontroller or etc. Is it okay? I am not discussing about those loops of microcontroller devices, etc. Assuming that you would be having enough this 5-day program, there will be some talk on microcontroller based systems for data acquisition, sensing, and then using it for various other applications. So I have skipped that part. However, I am expecting that you will learn it at a later stage in terms of digital to analog signal conversion, or analog to digital signal conversion, and then a microcontroller reading it or using it for actuation.
Okay, sir. Thank you. And we have one more question. What from Yashwant Kumar? What are the wide range sensors and actuators used?
You see, today I am not talking about actuators and sensors. Again, I am assuming that in robotics, in this 5-day course, there will be someone who would be talking on actuators and sensors. I can just give you quickly, because I thought instead of covering such topics, I thought if I can cover some other topics, particularly as I told you, related to such optomechatronic system, etc., because they are being advanced techniques and they will be useful for all of you to learn some advanced aspects. That's why I covered that. But I come back to your question that actuators can be in this such robotic systems. The actuators are electrical servo motors, DC motors, stepper motors, or in some of the systems, where very large amount of complex systems with large displacements, etc., are there, and linear displacements. Then sometimes they use hydraulic systems as well. So hydraulic actuation, pneumatic actuation, electrical actuations are the main aspects. Okay, in electrical actuation, it can be stepper motor drive, or it can be DC motor drive, or it can be other types of pulse width modulate based motor drives, etc. Okay, servo controlled drive. That is the main aspect. And sensors, of course, whole sensors are also, there are numerous types of sensors for position sensing. It can be optical approach, or it can be mechanical, magnetic approach, or electrical approach, maybe based on strain gauge, maybe based on capacitance, maybe based on linear variable differential transformer, right? Or if I want to pick up the speed, then there is optical techniques, or based on the induction pickup, right? We can easily pick up the signal, or Hall effect sensor based on the magnetic induction approach. So sensors are also numerous. Various other sensors are available, and various actuators are available. Although I'm not talking about it in detail at present, but they are altogether, again, right? I am sure in this robotics workshop, You would be learning short-term course. You will be learning about actuators, sensors at other place, right, within this short-term course. So I will not be able to cover now. I'll so with this this my answer is uh, this.
Thank you so much, sir. And now we have no more questions. I think you can proceed with the session, sir.
Okay, so I'll come back to our right. We will again continue with our some few more slides, right, before we go further. So there are now the light which I showed you some of these sensing devices. They are all free space optics, right? You could see that the light is traveling directly in the free space and trying to give you some information, either using position sensing device or by using LED coupled with some camera device, etc., which is trying to capture the free space of information. We can have light which can travel through optical fiber and which can be used to see through in terms of the information at some other position. So here these applications are also useful in order to capture the information which are not easily accessible in free space. Okay, so it can be coupled with endoscope, or it can be coupled with some robotic arm system which can help us to determine various other examples, which I will try to show it to you in the next few slides. Okay. So over here, the light what is used over here is basically trying to capture the interference light information. So light is transmitted through this fiber, light is getting transmitted through this another fiber, and then you see the interference fringe pattern over here. Now if some position, if some changes occurs along the path of this light or along the path of the transmission of the light in this arm, then if there is any change, and if then the interference pattern over here will change. Indirectly, we are trying to find out a micron level or a nanometer level small changes along this fiber arm, which can help us to determine the changes using interference pattern over here. So the detector over here will help us to determine if there is any change occurring over here. So this is one example. It is useful in measuring such fiber-based systems are useful to measure temperature change or pressure change along one of these arms, etc. Okay, so very precise, very small temperature change can be captured using this. Now there is another aspect. So this is purely optical, but the next page will give you the application it is being used. So here, for some of you, it may be a slightly a different topic, but I'll quickly explain you. This is nothing but an optical fiber. Okay, in this optical fiber, some grating structure is being written over here. Okay, it can be written optically, or it can be written with some other approaches, mechanical approaches. Now, when this grating structure is written, the property of this grating structure is such that it has a certain period. Okay, so this grating structure, if I see here, it has a certain periodic structure with a certain period lambda over here. And if a light with a wavelength, a certain wavelength comes, then depending upon this period and depending upon this equation, Briggs equation, the particular light which is coming in, part of that wave, some of those wavelengths out of light coming in will get reflected back. Okay, so some of the light will get transmitted. So if this grating period changes, then the reflected wavelength will again change. Okay, So if the grating period compresses, then the grating period changes over here. Accordingly, the wavelength over here will change. Okay. So indirectly, if I mount it right on some structure, then if the structure is expanding or contracting, I can capture its information, right, even though the fiber is built within the structure. So if I'll give you same explanation with little colorful way, I can give you that when light comes, let's say light is coming, which is a broadband spectrum consisting of all violet, indigo, blue, green, yellow, orange light. It goes through this fiber, and as I told you, that is within the fiber there's a grating structure. Depending upon the grating period, some part of the light will get reflected, while some part of the remaining part of the light will get transmitted. So if the grating period satisfies the equation, this Bragg equation, that particular wavelength will reflect back. So if yellow light is satisfying this Bragg equation, where n is the refractive index difference over here, and lambda is grating period of this grating structure. Sorry, not refractive index difference, but the effective refractive index based on the structure, and the lambda is the grating period of this structure. Then corresponding to that particular wavelength, green light, maybe yellow and green light is getting reflected, while transmitted light is remaining light, part of the light. So what you will see is one dip in this transmitted light and the corresponding reflection at the same wavelength over here. Now using this information, we can capture, right, whether the grating, what is the period of this grating. Now by any chance, if the structure is undergoing some deformation, the grating structure will change over here. Then the reflected light wavelength will change here, because the Bragg wavelength will change as the grating period is changing. And hence, we can see that the transmission spectra may change. So, we can have different grating structures, accordingly different wavelengths getting reflected. And wherever there is a deformation taking place, that particular wavelength will shift by small amount. And that means this is nothing but the distributed feedback it gives. I can capture the information from position 1 or position 2 or position 3 depending upon the grating period. Okay, so that can be captured. I can even measure not only the stress induced, even the temperature difference in the material can be captured using this wavelength shift, etc. Okay, so I can capture some of the information which are not seen easily, micron level deformations, but I can capture using such optical measurement technique, using optical fiber. Now here I am trying to show you something interesting application of this, which is nothing but the gyro, optical gyro, which is used in our space applications, etc. So the light comes in, and when it's going around like this. Okay, I am showing it to you with a very simplified figure over here. Okay, so light comes, it goes, and there are mirrors which will reflect the light. So this is a beam splitter, so it splits the light into two, and part of it goes here, and light goes, it comes here, it reflects here, it goes here, and it comes back. And the light which is getting reflected in this direction goes like this, goes like this, goes like this, comes and reflects. So light traveling in this arm and light traveling in this arm, both of them, they meet here. Now if there is any change in the arm characteristics, then you will see the interference. But in this case, the one which I am showing you, you won't be able to see the interference, because change in the interference, because even if anything changes in this arm, temperature or something else which changes the light traveling characteristics, then both the arms, see the light traveling in this arm will also observe such change, light traveling in this arm will also observe such change. So I don't see any difference in the light interference pattern over here. But when the system starts rotating, then light traveling in this, if the system starts rotating in this clockwise direction, then the light which is traveling in one arm, clockwise arm, will have to travel little more, as because the whole system is rotating. So this mirror, by the time light comes in clockwise direction over here, the mirror might have shifted by small amount because the whole system is rotating. So the light traveling in clockwise arm will travel more than light traveling in the anti-clockwise direction, because in anti-clockwise direction, by the time light comes to this mirror would have come nearer in this position. So indirectly, when this system is rotating, this type of optical fiber based system can capture the small angular rotation and can give us information about the angular rotation along this. And if I have 3 such arms, I can capture XYZ direction, right? Angular motion. It can capture the motion of the orbits. Although I am not showing you the calculations, etc., but I can tell you that it can capture the information of the order of the small angular deviation, right? In terms of milli degree also. Okay, very small rotation can be captured. Okay? So it has applications in missiles everywhere, etc. Okay, now coming to another application, I can also capture the information of the exhaust, automotive exhaust or power plant exhaust, etc. using such, or in diesel engine exhaust. I can capture, or in biomedical human breath exhale can be captured. All this information can be captured, and we can measure concentrations of different species of the gas. Here, one example is about ammonia. So if there is an ammonia presence, you will see such a signature of ammonia in the light which is getting transmitted. Okay, so depending upon the concentration of the ammonia, this intensity, the transmitted signal intensity will vary, and that can be used to capture the concentration of ammonia. Like this, we can capture the information of CO2 in a power plant or methane in a power plant, etc. We can couple it with the piezoelectric actuator, change the fiber grating right structure, and capture the wavelength which is getting absorbed by the spectrum analyzer can be captured. So, right? So there are tremendous applications of optical systems which can be coupled with various such mechatronic aspects, and the optomechatronic systems works in that way. Of course, there are some few more optical systems in free space. One, as you can see here, that here you can see, I'm sorry, I didn't put it in full screen mode maybe, but you can see that you can use radar microwave system to capture, or optical system to capture the position of the vehicle, to avoid right collisions, etc. You can make use of various other electromagnetic waves in order to capture the information, position of the car, position of the vehicle, side positions, right, etc. So we can use such optical techniques. We can use camera, and we can make use of optical sensors to position in different directions. Right, we can use remote sensor to position with respect to the obstacle, and we can also use camera system to measure other positions. Now we can make use of such mobile platforms for environmental sensing, for localization, by using laser finders, range finders, etc. So optomechatronics systems couples right mobile platforms having servo systems, servo drives, etc. And then those mobile platforms goes around along with laser range finders, optical sensors, and captures the environmental information, accordingly provides the feedback to the system. Now this is the first version, right, human guided vehicle, where human is using electrical drives to move the vehicle and position. But the next version can be automatically guided robot system, so which moves along the guiding well tracks, tracks, and picks up the workpiece or places the workpiece, unload or loads the workpiece. This is another free range device, no automatic guiding. It has various cameras and scanners, so it can move around freely in the industry around, and helps us for transport applications, right, workpiece movement applications, etc. And this is another extreme application. So another extreme application is we can make use of a system where in unknown terrain, right, a robotic system lands, let's say Mars rover, and then light illuminates this object, and when it irradiates this object, then it will get ablated by large intensity of this laser beam, and then there is a plasma generated. This plasma, when laser strikes, will produce some optical emissions of different wavelengths depending upon the species here. So if it is silicon, you will see some silicon emission lines. If there is iron, you will see iron emission lines. So that means we can characterize the rock structure, soil structures, etc. in unknown terrain, unknown territory, by coupling the laser systems for not only for mobile operations, but for even analysis of the environment, correct? So in short, we can integrate optics, lasers with mechatronics and optical sensors coupled with optical fibers, and use it for various mechatronics applications, not only in stationary conditions, but with autonomous vehicles, etc. So thank you very much for listening to me, and I hope you got some idea about how optical sensors, optical sensing devices are used for various such applications. With this, my presentation is over. However, if you have some other questions, you are welcome.
Thank you, sir. We have a question, sir.
Yes.
Question from Dr. Vidya Ganeshan.
Yeah.
Is camera required for robot? Many sensors and actuators are using to build. Then why we need camera?
Yeah. You see, the one which I showed you, the two applications which I showed you, one is to calibrate the camera system itself. Okay, so we can make use of a position sensor or a point sensor for positioning. However, sometimes redundancy while doing robot calibration helps in improving the positional accuracy and precision. That's where we can use such camera. In another application which I had shown you, the camera is not capturing the robot position. What it captures in, as I had shown you in one of the slide, in welding, it is trying to capture the weld structure which is getting welded. Okay, so the camera is trying to give us information about the weld structure which is getting welded. Now, point sensors or position sensors will not be able to capture the weld region. It can give you point or position, while camera can give you two-dimensional information, because it's an array of photodetectors which can give you the information about the weld met. Okay, so here robotic arm is doing welding operation. However, it is not right if we do not use any feedback system to provide feedback in terms of quality of the weld. Then it is very difficult to afterwards judge the quality of the weld by the robotic system unless we do destructive testing. But if we incorporate such systems, automatically it will give the feedback to the robotic arm regarding, oh yeah, there are some pinholes coming, or if the material feeding is not proper, increase the speed of the material feed, or increase or decrease the speed of the robotic arm. All such feedback can be given. For that purpose, we can make use of such optical camera systems for sensing purpose. Is it okay?
Thank you, sir. And one more question from Madhu.
Yeah.
Considering outdoor applications, what are the common practices to reduce the effect of changing ambient light?
Yeah. Okay. So generally, what is very simple? Of course, it's not only the problem with the ambient light. Ambient light control is possible by using appropriate filters, right? As well as using sensing devices with the light which is not commonly present in the ambience outside, right? I can use infrared light source to detect something, right? And infrared light which is available in the common ambience will not be so much to interfere. So that will be very easy to take care. However, the challenge is with the outside this part is the scattering of light. Okay, because if there are some dust particles or some, let's say, rainy particles or some other droplets which are there in the atmosphere, they may scatter the light, and then your intensity of the reflected signal may get affected. The angle of reflection, etc., scattering will come into picture. So those aspects becomes challenging. Another aspect is the absorption of those light, also optical light, right? So if there is a medium which will absorb that transmitted light through the medium, then your intensity again will get affected. So we should ensure that the optical light or optical sensor what we use should not get affected by such absorption or scattering, etc., and we can use. And as I pointed out, the ambient light control is using some filters and ensuring that you use some other light which is not exactly present in that ambience in order to sense the position, etc.
Thank you, sir.
Yeah.
And I think that's the end of the questioning session, sir.
Yeah.
And
Thank you so much. In case if you have more queries in the beginning of my slide, maybe I had given you my email address, so someone can even write to me. That's not a problem.
Sir, okay, sir. Thank you, sir. Thank you so much for sharing your knowledge. So, you can give me administrative, right?
yeah, sir. 1 minute, sir.
Okay, sir. So thanks for your timing, sir, and hope this might have given some input to the participants to develop further in this area as far as the research is concerned. And let us hope this will also help them to go for a better classroom teaching by this knowledge enhancement. And thank you, sir. Thank you. We'd like to hear a lot from in the summer occasions. And thank you for coming.
Thank you. I hope that I didn't cover purely robotic systems. I tried to cover something which can and complement because anyway I thought in 5 days time they would be very much involved in various robotic systems. I hope that's fine. It was fine. Yes.
Yes, sir. Yes, sir. Yes, sir. So certainly this will be useful, and this will help them to develop something, sir.
Thank you.
Yes,
Thank
sir.
you very much.
Thank you, sir. Thank you, sir. We will meet in some other occasion, sir. Thank you, sir. Thank you so much.
Thank you, sir. Right. Shall I come
Yeah,
out of
yeah.
the?
We can.
Fine. Okay.
Thanks, sir.
Thank you very much, sir.
Okay. So participant, thank you so much. And so once the session is over, you have to close this window, and again you have to open a new window. You have to click the link, and you have to go for registration for getting into the next session. Okay. So because attendance is mandatory. Okay. So hence, once this session is over, you close the window. Okay. You open new window and open and use the existing link to rejoin the next session. Okay. Then you will be able to rejoin. If you without closing this window, and if you are refreshing, so you will not be able to join the session. Okay. So you close the window and paste the link what we have sent. Then it will ask for registration. Then you have to register. Then one link will be displayed. That link can be used for joining the next session. Okay. So if any doubt, you can call us, or you can put a message through WhatsApp. And I request all of you to be in WhatsApp group. Okay. So that will be helping us to have a fastest communication. Okay. And thank you so much. In the next session will be practical sessions. So that will be started by 1:45. So that will be a very good session to learn how they practically how the robot is making a movement, and how you will be able to program it. So you will get a live demo in the Kuka Robotics. Okay. So please join us. Thank you.